All right, so for all you folks online, we are back on time again. So those of you who thought you're gonna get a 15-minute break later in the day, sorry, we're back on track with the agenda. Two quick housekeeping items I probably should have mentioned. If you have not figured this out by now, if you have questions throughout the next 2 days, myself, Mike Kosh, and Ron, if you wouldn't mind listing your hand, Ronald Leeper, are the ones to talk to with those questions. And I am, if you didn't figure this out, Elisa Senga, I'm the one who's been sending you large quantities of emails. So if you have a beef with me about that, come chat. But I prefer you just come say hi during any one of the breaks because I always like to meet all the folks that I haven't met before and see all the familiar faces again and say hi. This is a great community to be a part of. So we're going to move now into our keynote speaker for the morning. It is my pleasure to present Dr. Ali Ferris. He is a Texas A&M University System Regents Professor at Prairie View A&M University and a leading expert in soil moisture sensing with over 30 years of experience in sensor technologies and applications across land-grant institutions in Florida, Hawaii, and Texas, as well as industry experience in Australia. He has organized 3 international conferences on soil moisture and is widely published. His work focuses on applying smart technologies and AI to food, energy, water, health nexus challenges. And he has been ranked in the top 1% of scholars globally by Scholar GPS and has secured over 110 million in funding. Tell us your secrets. He has testified before Congress and contributed to national climate assessments and to the 2026 Presidential AI Challenge. He has also edited several books with UNESCO, Springer, and I never know how to pronounce it, the other one that starts with the E, Elsevier. And he holds graduate degrees from the University of Florida and a BS from Tunisia. Today, he's going to be kicking off this conference by talking about hazards broadly in relation to soil moisture. The title of his talk is Soil Moisture for Natural Hazards, Challenges, Data Gaps, and Emerging Data-Driven Opportunities. And he'll be talking today about how soil moisture is a key link across these natural hazards as well as public health, but how current limitations in measurement and application do still remain significant. He'll talk about scale mismatches and data gaps and how these exist alongside emerging advances in sensing, data integration, and machine learning to improve hazard prediction and decision-making. Please join me in welcoming him.
Thank you, Lisa.
And you can just back and forward.
Yes, thank you. Howdy. Thank you, Mike, and thank you also for the invitation. Thank you, Ron, for the invitation as well. It's a beautiful campus here. It's a beautiful day. I miss this type of environment in Hawaii. I mean, this is basically reminds me of great times in Hawaii as well. So I guess I think since it's fresh in my mind, the $110 million, I'm a PI and co-PI. There are lots of people who really did that numbers. It's not by myself. So give credit when credit is due. I guess it was back in 1996. I was fresh graduate from University of Florida, and then I offered a position as a postdoc position in the Citrus Research Center near Orlando there at the University of Florida. So my supervisor at that time, Shakalva, he introduced me to soil moisture sensors. I did my PhD on forest hydrology, so it was nothing to do with soil moisture sensing at that time. And he showed me these Syntax system at that time that monitor the water soil moisture at different depths in the root zone, below the root zone, every 15 minutes. And he said, I've been using this to schedule irrigation. I said, you have a gold of mine here. I said, what do you mean? I said, you can use a lot, you can derive lots of information from this in addition to scheduling your irrigation. He said, what can you do with it? I said, you can calculate evapotranspiration from these trees. You can determine your soil water release curve for this one. You can determine drainage and so on. So he said, are you sure? I said, yes, I will do it. So from that, we started working on soil moisture in that essence. I loved it. So when Syntec came to visit us, I told them what their sensor showed. Then they said, can you go with me? Can you go with us and work in Australia? I said, sure. let's go take a sabbatical before I get my faculty position. So, so I spent a year in Australia there doing that. So, and in I think in the early 2000s, Steve Avett, Sally Logiston, Mike Jackson, I'm sorry, all these people are working on soil moisture. We would like to have a conference where we can discuss just soil moisture alone. So I was faculty at the University of Hawaii. We started the first conference in 2007. And then 2012, we had the second conference. And when I moved from Hawaii to, we had in 2014, another third one in Houston. I think Mike was there and other people. So, and I got busy with administration and other things, so I left soil moisture for a while, but I never left it. But we still continued working on soil moisture. So I think to give you this background about a journey, so I'm very pleased. I really very pleased to see that Congress recognized the importance of soil moisture in this arena, and then there is this annual meeting that I've been trying to come, and I'm pleased to be here this year. So let's talk a little bit about soil moisture and natural hazards. And thank you, Mike, and thank you for giving some of the feedback about making my presentation a little bit easier, because that's some of the topics that I would like to discuss. By the way, I have a book that I just edited with Elsevier about this is global drought and sustainability. So this just came out in March. So I have a QR code, and also there is another book coming on AI and water, energy, food nexus this October that it's on the table. But Mike, you can pass it around if you want to. Ron. Anyway, so let's get into the presentation. So I'd like, yeah, I don't want to move far away from here because of the online audience. Okay, so I guess I will discuss soil moisture as Mike mentioned, the most important variable for understanding natural hazard, water security, and also environmental resilience. I will share lessons from observation, case studies, and recent advances in artificial intelligence, and conclude with a vision on how we can transform environmental observation into actionable intelligence, and that supports better decision and more resilient future. So this is the outline of the presentation, why soil moisture matters. Also, scientific foundation about soil moisture in general. I would like to keep my time on so that I don't want to go over. And also soil moisture through the lens of hazards. Evidence from some of the case studies that I'm going to go through, and some from data to intelligence, I think right now, and a vision, a brief outlines of what we think for the future. As it was mentioned before, these are two different natural hazards: severe drought, wildfire, major floods, and landslides. What do these hazards have in common? The central theme or the central link in there is soil moisture. The lack of or the excess of, right? So that is the common thread in this issue. And disclaimer, I also use AI to illustrate some of these things. So I teach my students, and I encourage them to embrace AI. So I said, let me be one of the users. So at least, so they give credit also for these AI tools as we go. So why soil moisture matters? Because you don't see soil moisture, right? Surface water, you can see it. Snow, you can see it, but you cannot see soil moisture. It's a hidden. So understanding the hidden variables behind droughts, behind floods, behind wildfires, and environmental resilience. So the goal is to go from monitoring. We spend decades monitoring soil moisture, basically trying to provide the best sensor for the best location and accuracy and so on and so forth. So we have to go from that on how to measure soil moisture into the needs or the tools of using soil moisture. So the question of today is, how do we transform soil moisture into intelligence to help us with some of these issues of dealing with natural hazards, or dealing with food security, or dealing with air quality, as it was mentioned before, dealing with all these issues that we are facing day in and day out. So soil moisture has evolved from a hydrological state variable into a strategic indicator for understanding and predicting natural hazards. How can we, if we know the soil moisture, we have a good grasp on soil moisture, quantity and variability, etc., and function of time and space, that should help us predict some of these hazards. Research over the last decades, as I mentioned, has demonstrated its central role. People are convinced right now that soil moisture is an important component of the hydrological cycle in drought development, flood generation, wildfire susceptibility, and climate feedbacks. Advances in sensing technology, remote sensing, modeling, and artificial intelligence are transforming monitoring capabilities. Right now, you can have it's just what scale you want to. And that causes also a problem also at the same time, because not all the time what the satellite's information gives you will coincide or would agree with in situ measurement or with your drone measurements or your. So how can we reconcile that variability there? So advances in sensing technologies and also AI are transforming monitoring capabilities. We are luckily, and I like that slide about the bunch of numbers that you see there, lots of numbers to handle, right? Imagine if you have a soil moisture sensor that collect every 15 minutes a value of the soil moisture, and you have hundreds of them. All those numbers, we have to make a story out of that, or some decision about that one. So that's where AI and other tools can help us in that process. The challenge today is not simply measuring soil moisture, but converting observation into actionable hazard intelligence. So let's see moisture sensor through the lens of hazards. How a single variable influences drought, flood, wildfire, and what we call cascading effect. So you have one event that will lead to another event. You have a drought that results into a fire, and then comes some torrential rain, heavy rain. It becomes like a mudslide, become landslides, and become disaster, another disaster at level. All of them are coming one after the other because of what's happened. Why soil moisture matters more than ever? Many hazards become predictable only when antecedent soil moisture is known. So if you tell me that today we received 2 inches of rain here in this mountainous area, I can tell you there is nothing happened. I can tell you it can be disasters as well. The difference between the two is what's the status of the soil moisture of your landscape. If it was already saturated, so any single drop of water is going to come, what's going to happen? What's going to happen? It's going to end up as a runoff, right? But if it is dry, then the conditions are a little bit modest. So this is what we do in hydrological. We need soil antecedent soil moisture is a key in understanding what's or predicting what happened. I'm sorry. Let's go back. So hazards, flood severity depends, as I mentioned, strongly on the amount of water already stored within the soil profile. Drought development reflects the progressive depletion of root zone water reserves and their interaction with vegetation. Wildfire susceptibility, when you predict, or the modeling of predicting fire potential starts with soil moisture, is increasingly linked and persists soil moisture deficit and vegetation stress. So you have to have fuel, and you have to have the conditions that are incentive to that one. So soil moisture and the national agenda, as I was mentioned about the national coordinating soil moisture network. So that initiative is great. I mean, it's fantastic, and I kudos to those who really worked on that. Mike and colleagues really appreciate that. Soil moisture is becoming a national environmental infrastructure. So was established to develop this network was to establish a coordinated national soil moisture capability. This initiative promotes integration of in situ location observation, remote sensing products, and model simulation into operation information system. So how can we use all this rich information that we have about soil moisture and the modeling capabilities as well, so we can really have some nice products that help us address some of the issues. Application include drought monitoring, so you cannot predict drought without knowing the soil moisture. You need to know that. Flood forecasting, wildfire preparedness, water management, how to manage for your water, as if you are in agriculture, or if you are in city, urban areas, whatever the water need be. And as it was mentioned right now, we add to that is the data centers. I mean, it's a big issue we have in Texas right now, because data centers are popping out all over the Texas. I mean, and strong dialogue and very healthy and dialogue about what's the role of these data centers on water security of the state as a whole. Yes, they have the economical component that we cannot ignore, but also they do have some footprints and they have some impact on our water resources. How can we have these data centers with the least impact on our water resources? And of course, a state like Texas is prone to drought, and we have to deal with drought all the time. So these are some very interesting topics and very interesting at different levels on how to deal with these, because they have connection with water. Its vision extends beyond measurements toward a national soil moisture intelligence framework. So we go back to basic different hazards depend on different parts of the soil profile. So as a soil scientist myself, soil is a key. When you talk about soil moisture, of course, the soil is the place for this discussion to happen. So the soil profile has different function in many ways, in production in other areas, but also on soil moisture as it relates to our topic right now. So if you are talking about surface soil moisture, primarily influences infiltration, influences the runoff generation, and flood response. If you go a little bit deeper to the root zone moisture, governs vegetation stress, agriculture productivities, and drought development. If you go a little bit deeper, influences groundwater recharge. So if you talk about groundwater recharge, you're going to talk about the process of water moving down below the root zone, 2 meters, or depends on your root zone. So plant available water often provides more useful information than total water content for ecosystem application. Because if you tell me that the soil moisture content is 10% per volume, I can tell you your plants are dying if it is a clay soil, loamy soil. But if it is a sandy soil in Florida, 10% is your, I mean, you are thrilled, because that's the field capacity of your sandy soil. So the value doesn't give you because there is a missing information, which is the soil type. So the soil type is a very important, and the availability of water, the water available, and some of these sandy soil is only, as I said, if it is 10% or 9% your field capacity, permanent melting point is 2%, right? You're only working with 7 to 8% of water. But if you have a better soil, you're working maybe 25%, 30%. So you can see, even from irrigation management, this is what we teach people, is like, if you soil variability around the field, if you have some part are heavy clay or clayish, another sandy, you cannot irrigate them the same way, because that sandy soil in 3 days, it will be permanent wilting point. The other soil will be still happy. The plants are growing and doing very well. So it's very important that we know the soil type that we are dealing with when we deal with soil moisture. Effective hazard prediction requires matching the appropriate soil moisture metric to the process of interest. So if you are interested in groundwater recharge, you are more likely interested in the deeper soil profile than you do in the upper soil profile. But if you are, as I mentioned, dealing with other issues, then you have different interests. So soil moisture why soil moisture is a hazard variable. Hazard often depends on an antecedent, as I mentioned earlier. Some of these points are already mentioned. So saturated soil can transform moderate storm, as I mentioned earlier, into major floods. Dry soil can accelerate drought development. So persistent soil moisture deficit increase vegetation stress and reduce ecosystem resiliency. So those ecosystems becomes very susceptible to fire, very susceptible to many other disasters as well. So that soil moisture acts as preconditioning factor that determine vulnerability before hazards occur. Drought develops in the soil before impacts become visible. You will, if you would like to manage drought, you don't wait until the plant is wilted. It's too late then. You have to monitor your soil moisture so that you know that in a few days that you need really, those plants are going to be either dead or you have to do an action there. That's why irrigation scheduling, we have to do it through the soil much better. So root zone observation are increasingly important for drought forecasting. The future of drought monitoring lies in understanding soil water storage rather than rainfall deficit alone. As I said, depends on the soil type. Just predicting irrigation management or other things based on rainfall alone is not enough. The soil moisture and the soil profile should be very important. So
your slides have stopped showing that.
Okay. Thank you. So rainfall alone does not determine flood risk, as we mentioned, depends on the event. How saturated is your soil? So understanding the storage dynamic is essential for future flood resilience. The same thing for wildfire. Soil moisture emerging as a critical wildfire indicator. Long-term soil moisture deficit increases vegetation stress and reduces fuel moisture. So integrating soil moisture with vegetation indicator represent an important frontier in the fire science. That's the main idea there. Measuring the invisible, because it's, as I mentioned, soil moisture is invisible. So a drought can increase wildfire risk and alter ecosystems. So compounding hazards highlight the need for integrated environmental intelligence system. So where you integrate soil moisture with rain, with the soil type, with the plant growth stage, etc., so that we can determine a best way of addressing wildfire and for instance, and other hazards as well. So as it was mentioned, also soil moisture connects the water, energy, and carbon cycle. There is a nexus there. Soil moisture regulates the partition of precipitation into infiltration, runoff, storage, and deep ground recharge. It controls evapotranspiration and therefore influences land atmosphere energy exchange. Also, a few environmental variables simultaneously influence hydrological, ecological, and atmospheric process to the same extent. I guess measuring the invisible, again, I talked about this point, and for sake of time, I would like to talk about scaling. How can we scale up or scale down? Can we use the in-situ soil moisture monitoring to scale up and at larger scale, or can we do the reverse? And lots of work has been done in that area. Okay, and still there is more work to do, because we would like to use all those tools that we have, the satellite products and the in-situ products and the network that you have seen. We have satellites also that orbit the Earth and monitor the soil moisture. And that's how it come to my case study, the first one. This is work that we did in Prairie. My colleague Ray led it, and with me and her and Tamimi in Stevens College. So in this one, we compared 4 satellite products to in-situ soil moisture and try to see relationship between the two. So in this work, we compared, as I mentioned, these photo satellite across hydrological area in Texas there. We have 10 hydrological area where distinct. I mean, as you know, Texas on the east side is wet and the west side is dry, and also and in between. So you go from more than 50 inches in the east side of Texas, you less than 10 inches in El Paso. So there is that gamut of variability in weather and of course of ecosystems as well and soil types. So it's a fascinating environment to do hydrological work, to do work in this area because of that variability. So we use these 4 satellites. So the bottom line was of this study was that SMAP was consistently produced the strongest agreement with in-situ. So we compared satellite with in-situ. SMAP was the SMAP satellite that was launched by NASA in 2015 was the best. And you can see the other performing satellite. So that means there is variability even with the satellite products. So what are the data gaps and the root zone problem? The greatest observation gap lies beneath the surface. So as I said, most satellite, they only see the top 5 centimeters. Many hazards depend on root zone conditions extending much deeper than the vadose zone. Forest, for example, mountains, rangeland, and dry remains under-monitored. Those areas, more work needs to be done in this area. Long-term records remain sparse and many environmentally sensitive regions. So you see lots of data that has been produced. I mean, how's the best way to handle that data sets? How to best to store that data sets so that we can have historical information that can be useful for us to do long-term studies that needs historical data. Closing these gaps is essential for improving hazard prediction. From measurement uncertainty to forecast uncertainty. So we have been doing a good job in matters. How about forecasting? Forecasting quality depends on observation quality. You cannot forecast the future if you don't have a good quality historical data that you can rely on to help you predict the future. So sensors, they respond to temperature, salinity, texture, organic matter, all influence measurement of our soil moisture, how to handle these data. Calibration remains another issue. Sensor uncertainty propagates into models and forecasting systems. So if you have error in your data that propagate with models, etc. So a future monitoring system must explicitly quantify and communicate uncertainty. That's very important. So we would like to share with you another quick example. This is the Uri storm that hit Texas and hit most of the US, I think, northern states, but impacted us severely in Texas. And we had a failure in the gas distribution, and then the power plant failed, and then the water system failed, and then we don't have food because grocery store cannot get supply, etc. So these effects cascaded starting with a snowstorm and cascaded to other problem, etc. In this study, we acknowledge that one, but we said there are maybe positive also of these winter storms. So we quantified, and before that, Texas was in a drought. So we investigated how this snowstorm impacted drought relief for the state of Texas. So the idea was, this is, as you can see, this is the drought map in the February in the left one. The one after the snowstorm, and this is below the snowstorm. So the main message of this is that winter storm relieved the drought of the state for at least for a month or so. So that was some positive of that cascading effect, which basically, because of those records of 2 to 4 inches of rain/snow across that resulted in a basically, the storm equivalent during the event showed a higher correlation with daily root moisture in the long term. So another case study where I don't know, how are we doing, Tom? 2 minutes? So I think I'm going to go to the vision here. I think to the last few I think this is an important slide that I would like to share, is real-world cascading hazard sequence. This happens several times in California. This is one example. The mega drought between 2012 to 2017. Then the Thomas Fire in the South California happened in December, January 2018. After that, the atmospheric river events in January 9th. And then the Montecitos debris flow and death of people and billions of dollars of disasters, impacts on the infrastructure. So these are cascading because of the soil, a drought, etc. So this is an example of how this. So I think it's one of the. I would be remiss if I don't talk about AI since and this topic. So AI and soil moisture. AI is transforming environmental prediction. Machine learning can improve retrieval forecasting, downscaling, and gap filling. Data-driven approaches can identify relationships difficult to capture using traditional methods. Physics-informed AI provides a pathway for combining process understanding and data science. Explainable AI will essentially be for operational adaptation. Future forecasting system will increasingly integrate AI with physical models. There are lots of opportunity there. Also given the caveat that, as we all know, AI hallucinates. So we have to have very good check and balances of the data produced through AI. Digital twins, another use of AI, also very, very helpful because it revolutionized numerical modeling in general. In numerical modeling, we used to do numerical model, give the output, then this digital twin helps you give real-time data as you simulate, so to improve the performance of your models. So really revolutionized numerical modeling and helps us, give us tools that are really more accurate than the traditional modeling that we have been doing. So there's a lot of potential in that area as well. I think a vision for the future, research priorities for the next decade. The next generation of soil moisture science must be hazard-driven, integrated, and operational. So observe below the surface, expand monitoring of root zone and vadose zone dynamics, develop hazard-specific indicators, build national standards, advance AI and data assimilations, and benchmarking against outcomes. I think a vision for the future, from monitoring to soil moisture intelligence. The future is not simply building more sensors. We have enough sensors, I guess. This national coordinating soil moisture monitoring network vision of coordinating network of networks provides the framework for transforming fragmented observation into a unified national capability for hazards monitoring and forecasting. This is a great initiatives. Future systems should function as a real-time environmental intelligence platforms. Digital twins of watersheds, ag system, and landscape will increase, rely on soil moisture as a core state variable linking weather, ecosystem, water resources, and hazards. By 2035, soil moisture could play a role analogous to that of the weather observation today. When you forecast the weather, you can forecast also the soil moisture as well, providing the foundation for routine environmental forecasting, early warning system, climate adaptation, and national resiliency planning. So, for example, there are plenty of opportunities in this area. So, to close, for decades, the questions was how to measure soil moisture. Today, the question is how to transform soil moisture into intelligence. The future of the field will not be defined by sensors alone, but by our ability to integrate observations, models, AI, and decision system into a national capability that helps society anticipate and manage natural hazards before they become disaster. I think these are some of the references I used. I would like to thank you and thank this work was made possible through the support of funding agencies such as USDA and NSF, and also through talented and team. I would like to thank the Food, Energy, Water Nexus team for their members for their dedication and hard work. And thank you for listening to me, for this opportunity to present to you. I will be happy to entertain if you have any questions.
We do have time for a couple of questions, and I'm going to ask you to repeat the question before you answer it so the folks online can hear. And if you're asking a question, just speak up so that we can hear it.
Yes, sir.
You mentioned the need for national standards. Can you elaborate on what specifically?
Well, I think national standards, for example, what's a measurement acceptable? If you give a sensor gives you a value, for example, what's acceptable so that we can translate that information, because we're going to make a decision based on that one. There is uncertainty for that measurements, plus or minus what? What level should we be comfortable with? So, for example, if you can see that some of these values that we show comparison is you'll have a root mean square error of 15% for soil moisture. As I said, 15% for a sandy soil is a lot, but maybe for another soil type is okay, acceptable. So these are the type of I think standards I'm thinking about.
We have time for one more question if anyone else has one.
Yes.
So you mentioned digital twins. So what scale are you thinking is appropriate? Because to go to fine and so much you can vary at fine scale.
That's an excellent question. Digital twins. Oh, I'm sorry. Thank you. The question is about digital twins. Which scale is more appropriate? I think it depends on the use. For example, if you're talking about agriculture production and farm level, so that's the farm level. If you are talking about watershed, that's a watershed level. If you are talking about flooding, it's at the regional level, it's much more wider. So it depends really on the use or on the applicability of what you are trying to do.
Thank you.
Welcome. What?
Thank you very much.
You're welcome.
For your talk. We appreciate it.
Thank you. Thank you.